So I'm here with Alex Appel, aka Diffractor. So Alex, thanks a ton for chatting with me today. We're going to chat a little bit about the new mathematics that you and Vanessa Kosoy worked together to create to help us out with theoretical alignment. So I guess my
I should probably mention that a moderate chunk of this stuff was already present back in imprecise probability theory. That's sort of the pre-existing stuff about this, although we wound up independently reinventing most of it, which, although there is one particular part where it differs, and that is how updating is treated. That if you try to update a set of probability distributions and end up with a set of probability distributions, that's the wrong thing to do.
Right. So is it right to say that, yeah, I think I'd heard this before, that you and Vanessa didn't know that much about imprecise probability theory before you started working on infra-Bayesianism, and then you kind of independently
we started it, and eventually we were like, you know what, let's take a imprecise probability textbook and see if we can find anything interesting in it. And there is a substantial chunk of stuff we had independently worked out, and a few interesting things that we hadn't.
Yeah. Well, I had this question a little bit later, but now that we've gotten into the realm of where I think, yeah, it makes sense to ask this question now. How does one go about inventing new math? Like, what process did you and Vanessa follow to come up with IB? Like, I just want to know a little behind the scenes.
So in terms of actually creating the stuff, I would say that Vanessa has definitely a higher level of mathematical ability and creativity than me. I worked a lot on the proofs because I have a higher tolerance for typing stuff up. But the actual process is mostly just poking at stuff that doesn't really make sense. So here's the interesting thing, is that for proofs, a lot of the times, if you can see, the hard part is noticing that something is even there to be proved. And once you can see, hey, this might be a proof, you're usually pretty close to figuring it out, except for in a couple cases. And so it's sort of an iterative process of talk over stuff that doesn't really seem to be making sense, work it out, write up some proofs. There's some more stuff you probably uncovered in the process. Work it out, make some proofs, some more stuff won't make sense, and just keep following leads of stuff that feels tractable.
Yeah. And how did you get interested in Informationism in the first place? Like, how did you hear about it? How did you get on the train?
Vanessa had a bunch of personal posts about some of her stuff with like sets of probability distributions, and I made a comment at one point, I think near the start of the pandemic, before we even realized it was a pandemic, that, hey, you keep writing posts about this, but like, it seems rather sparse. The formalism seems rather sparse. How about I just like team up with you? We crank out a post. We can get it out in like 2 days. You know, just tell me what sort of basic stuff we want to prove, and we'll just get that post out. And then, as it turned out, as we were working on it, we realized, hang on, this doesn't really fit together. And well, we worked some more on it, and eventually, I think I can go back and find the actual Discord conversation. We wound up hitting the actual thing, which is the infra-Bayes update rule. And I noted that it seemed like a pretty big deal. And so we started working on it more and more. And there were a lot of failed attempts at drafts where like you get 2/3 of the way through and then, oh, whoops, we discovered some more stuff. So it wound up being kind of long. And the interesting thing is we actually started figuring it out from the perspective of trying to generalize imprecise probability theory to environments. And we actually had to sort of back up and realize, oh, wait, even though we started with environments, all these results are phrased much more naturally in terms of generalizing probability theory.
Yeah, gotcha. And what kinds of people do you think would be best suited to work on doing novel research in IB? More people like you and Vanessa with really strong theoretical math technical backgrounds, or do you think there are some skill sets that some new skill sets that people could bring to the table? Yeah, what kinds of people do you think would be well suited to work on this particular research direction?
It depends on exactly what standards you have for strong math skills. There might be some illusion of transparency thing where whatever level of math skill you have feels perfectly ordinary from the inside, but not so much from the outside. But I would say that at the current stage, what feels more promising is having enough of a background to start finding concepts from standard probability theory and getting interesting analogs of them. Like, we started out just trying to generalize taking expectations, but if you keep going in that direction, eventually you figure out, oh, hey, we can generalize entropy. Oh, hey, we can generalize taking the mean. And so I think that there's probably a lot more stuff left to find in terms of like, what's the imprecise probability theory analog of a Gaussian, maybe.
Gotcha. Yeah, and so it's a very similar question to that. So I just asked, like, what kinds of people would be most well suited to actually make research progress within IB. What kinds of people do you think should be working really hard to add the existing infra-Bayesian techniques to their toolkit so that they can use it to work on their problems? Like, what kind of people do you think would find infra-Bayesianism most useful in their research?
I think that most of it would be for areas where it feels like standard, if there's any area where it feels like standard probability distributions just aren't quite getting the job done. That a lot of times you would be using standard probability theory, but there are a couple things for like agents thinking about each other. Yeah, agents thinking about each other, value learning. So yeah, they're basically, if it feels like standard probability distributions aren't quite getting the job done because of maybe like the realizability problem or being too aggressive for optimizing or that sort of stuff, then it's probably worth poking at what happens if we generalize this. Do things get any better? Because there are a few things that you can do in InfraBayes that just do not have a standard probability theory analog.
Yeah, so I've got a few follow-up questions to that, but one, I want to backtrack just a little bit and just give you a chance to talk about, just in a nutshell, what is Informationism? How would you describe it in a nutshell to someone who has just heard this term and doesn't know anything about
it? Generalizing probability theory to I'd say probably a very big part of the story is that it isn't just like crisp logical reasoning, like first order logic, and worst case reasoning and probabilistic reasoning, that they're all different things. That there's a very important sense in which you can hybridize probabilistic reasoning and worst case reasoning, and this is basically generalizing probability theory to that setting. And it's probably one of the things I'm most excited about is that it shows that worst case reasoning can be smoothly meshed with probabilistic reasoning, and it's actually sort of a stable way to build an agent, that you don't automatically have a pressure for everything to be purely probabilistic if it started out non-probabilistic. There's a sense in which a worst case reasoner endorses continue to be a worst case reasoner.
Yeah, and so backing up to something that you said just a minute ago, how does meshing probabilistic reasoning with worst case reasoning in this way, how does that help us get a handle on agents who are thinking about each other, for instance?
So I will remark that for some cases in standard game theory, you you might assume that the opponent is somehow correlated with yourself, that their choice of probability distribution depends on your choice of probability distribution, or you might be, oh, it's an adversarial foe that might be smarter than me. I don't necessarily know exactly what they're going to do. I have rather a set of probability distributions, and I want to have some response that gets good coverage over this set. And that's an instance of why it shows up. That another way of thinking about it is that it generalizes, is that you can think of it as a generalization of probability theory to adversarial environments, or potentially adversarial.
Got it. Yeah. One question that I have is, are we working on, or are you working on Informationism because you predict that AGI will be the kind of agent that reasons using Informationism? Or are you working on Informationism because you'd like to somehow make the AGI reason using Informationism? Does that make sense?
Oh, yes. So I don't personally have particularly strong opinions about whether ordinary probabilistic reasoning is going to be enough. I think that Vanessa might have stronger opinions about that than I do. But I would say that it looks like an interesting possibility because of A, getting around the non-realizability issue, and B, because it shows that there's a stable way to build an agent that, instead of optimizing really hard on the stuff that looks best over it for its utility function, will do some sort of worst case reasoning of, I will take a probability distribution over actions that does pretty good for this set of possibilities. I think that getting a handle on that latter thing might help out with some value learning stuff.
So it sounds like you're saying that second thing that I said was
Yeah, the second thing about, I think it would be helpful if you're trying to make a more cautious AI, I guess, but I don't have particularly strong opinions personally about whether purely probabilistic stuff on its own is enough to get you to AGI.
Gotcha. You've mentioned value learning a couple times, and I think this will probably feature prominently in your answer to the next question, which is, yeah, in your view, how does Informationism help us prevent existential risk from advanced AI?
Yeah, so on my personal view, Vanessa would probably disagree with this. I think that she would emphasize some other stuff than I would, but on my personal view, probably one of the exciting parts, one of the most exciting parts, is that there is a stable agent design that has a set of possibilities, tries to optimize pretty well over all of them, and doesn't single out one in particular or just a probabilistic mix of all of them as the thing to optimize super hard for.
Yeah, so the idea is that if you're doing value learning and you are trying to get the AGI to optimize some objective function, instead of having to get the one objective function exactly right in the sense of outer alignment,
you can have a set of objective functions that haven't been conclusively ruled out and have a probability distribution over what to do that does acceptably for all of them.
Right. Yeah, any other paths to helping prevent existential risk that you see for Informationism, or is value learning like the main one?
It feels like the main one, but I do think that my opinion differs somewhat from Vanessa on this, so I think that you might want to get her opinion separately.
Sure. Yeah. I'll be talking with Vanessa as well, so I'll get her perspective too. Now, okay, so the next question is, how worried should we be, or not worried, that information research could help speed up AI capabilities research, right? If AGI isn't possible without dealing with non-realizability, and if IB successfully deals with non-realizability, then does informationism get us closer to AGI? Yeah, how do you think about this?
It strikes me as something that's kind of uncertain and that we have discussed a bit. That basically, me and Vanessa seem to have somewhat different opinions on the level of risk associated with this research, and I think that probably the sensible opinion is that, if you can talk a researcher into it, basically doing the non-disclosed by default thing of if it's, if it seems like basic fundamental research, that's probably fine. If it's like, hey, look at me, I slapped together this stuff with this probabilistic circuit stuff and made something that does really good on a bunch of benchmarks, that is something where if you do it, you probably should not tell people you did it.
Gotcha. So you're saying that just putting together the foundational math concepts does not strike you as that risky, but if you were in fact able to leverage IB to create an agent that's doing really well on benchmarks, then probably best to keep that under wraps.
Yeah, that there seem to be parts of this that are either pretty mathematically, that are either pretty neutral or that are essential enough towards further safety research that you might as well get them out. But it does strike me as the sort of thing that might be usable for capabilities stuff. Although, obviously, if there were any such directions, I wouldn't be mentioning them.
Gotcha. Now, one thing I just realized is that we've been using this term realizability and non-realizability, and we should probably define it. So how would you define in a nutshell what the problem of non-realizability is?
The problem of non-realizability is that under the standard formulation where you have a bunch of probability distributions over stuff, where the environment is big enough and complicated enough that none of the hypotheses in your hypothesis space are an exact match to what's going on.
Yeah. And why is this a major problem for, why is non-realizability a major problem for doing good reinforcement learning?
It's mainly because I would ideally want something that can exploit whatever structure is there in the environment to be exploited, even if it does not have, even if that particular environment structure doesn't make predictions about the entire rest of reality. That's one of the issues, is that you can't have partial hypotheses that just make predictions about the weather and remain agnostic on all the other stuff. And this sort of seems like the natural way to have partial hypotheses.
Great. So switching gears just a little bit. So there is a bunch of research that goes under the title of Informationism. You and Vanessa have written up a bunch of posts and proofs about Informationism. And there's also Information Physicalism, which is kind of an addendum to the basics of Informationism. So in a nutshell, this part of the conversation might get a little more technical, which is fine. How would you describe Information Physicalism in a nutshell?
Information Physicalism would probably be using the basic infra-Bayes framework to follow up on an idea about how to have naturalistic hypotheses that don't single the agent out as anything particularly special. And the fundamental mathematical operation that makes it tick, the bridge transform, is one of those things that does not have a pure probabilistic analog. Just probability distributions aren't enough to get it to work. And so, yeah, that's basically what I would say, using infra-Bayes as sort of the fundamental underlying tool to get a further idea about having naturalistic hypotheses to work out.
And yeah, can you just expand a little more on what you mean by a naturalistic hypothesis and what you mean by like an agent that doesn't occupy some privileged position in the universe? Just expand on those concepts just a little bit.
Okay, so for the standard framework for reinforcement learning, you have the agent as something completely separate from the environment that interacts with the environment by a defined input-output channel, and you can't have anything like, you drop a rock on the agent and it dies. And so a naturalistic hypothesis would be a hypothesis that's more like just here's what's going on in reality. The agent is not a particularly singled out part of this. But then that introduces the problem of, okay, if you like take an action or make a decision, what parts of this computation that doesn't have you as a special singled out part, how do you know what to change in it? So that is basically the issue it's trying to address, is trying to come up with something better than the standard reinforcement learning framework that doesn't assume the agent is a special part of the environment that is immutable.
Got it. Could you maybe give me an example of a hypothesis that would be phrased from the subjective perspective of an agent versus a hypothesis, maybe the same hypothesis with the more, bird's eye view perspective of the universe?
Maybe like throwing a towel over the webcam of an agent from the subjective point of view. It'd be like, okay, I'm suddenly seeing all black pixels. It's actually a pretty low complexity hypothesis that, if I suddenly switch to all black, then my webcam will be all black forever. It takes pretty little K complexity to have that as a hypothesis. And the more objective view is I don't particularly expect any reason for the universe to stop existing when somebody throws a towel on my webcam.
Yeah.
But from the subjective point of view, seeing all black forever is a very simple sort of event to specify.
Right. So I'm going to just throw out some technical language and symbols that show up in information physicalism here. In the videos, people will have seen Connell and I define these terms, so they'll have some more context. But here, I'll just go ahead and ask you. So an infra-Bayesian physicalist hypothesis is in the space box phi cross gamma. Is that right? It's an infra distribution on phi cross gamma.
You probably should actually edit a little thing into the screen with that, because it's very, very difficult to describe math in text. But yeah, I would basically say it's a joint belief on how physics is and how math is, in the sense that maybe there's some computation about the weather, and you would expect the actual behavior of the weather to be correlated with the computation. You'd be like, all right, I don't really know what happens if I run this computation of the weather, but I do think it's correlated with how the weather's actually going to work.
Got it. Yeah.
So joint belief over physics and math.
And can you give me an example of just an element of phi, which is the state space?
The state space, if I am remembering this correctly, is something like what each computation outputs. So each element. Oh wait, hang on. Phi, the state. Oh, you said phi, not gamma. Okay. So here's the cool part. It can actually vary with the hypothesis. You can have different state spaces for different hypotheses. You can have one state space that's like, all right, we're going to describe what type all of these atoms are and where they all are. You can have another one that's phrased in terms of quantum fields. You can have another one that's phrased in terms of macroscopic properties. It's unique to the hypothesis. There isn't one universal phi that must be a state space for everything. Every hypothesis can have its own phi.
I see. Okay, gotcha. So an element of one of those phi. So it's phi conditioned on what your hypothesis is. So an element of one of those.
Yeah, an element of one of those is basically just a description of like what happens in the universe.
Okay, so some set of laws of physics. Is that the idea?
Maybe not necessarily set of laws of physics, more like set of ways the universe can be.
Okay, gotcha.
Phrased in whatever ontology you want, really.
Yep. And now moving on to gamma, can you give me an example of what an element of gamma might look like?
So an example of that would be, let me think. Okay, so an element of that, if I'm remembering this correctly, is sort of telling you like what all the Turing machines do. Like, oh, this Turing machine spits out a 1, this one spits out a 37, whatever. So that's basically our version of how math is how did the computations turn out?
I see. Yeah. Okay, so we've got these two examples. We've got an example of something that's in phi, the state space. We've got an example of some element of gamma, the computational space. And if it's possible, could you give just a simple example of a physicalist hypothesis? Something in the space box phi cross gamma.
Probably one of the simplest ones is a single computation that you think is correlated with whether a particle is on the left or right, but you have total uncertainty about the contents of that computation. So you're like, I have literally no idea whether this computation is going to return a 0 or a 1, but I think that if it returns a 0, then this particle is on the left. If it returns a 1, then this particle is on the right.
Got it. Yeah, that's super helpful. Now, in information physicalism, we use a simplicity prior. Is that right?
Yeah, simplicity prior is sort of the obvious thing you'd hook up to it.
Yeah. And can you just define what a simplicity prior is, just for sake of completeness?
Simplicity prior is basically just any sort of probability distribution on hypotheses that assigns lower and lower weight to more and more complex hypotheses. And this might be a bit of a personal opinion, but I think it's kind of a vacuous term because you basically have to have a simplicity prior because there's a lot more complex hypotheses than simple ones. So, of course, you would have to have complex hypotheses have lower probability than simple ones to get all your probability to add up to 1.
I got it. Yeah. And I guess I think of the simplicity prior as a kind of enforcing a way to enforce Occam's razor on the agent. Does that seem accurate?
Yeah, I would say that Occam's razor is basically describing the simplicity prior assumption of Occam's razor is describing the simplicity prior insights of, oh, hey, there's a lot more complex hypotheses than simple ones. So any particular complex hypothesis has to have much lower probability than a simple one for like any sane probability distribution to add up to 1.
Nice. So at this point, I think it makes sense to go back and look a little bit more closely at something that you brought up a little earlier, which is the bridge transform. Why is that? We don't have to get too in the weeds on the math behind what the bridge transform is, but why is it useful? Why would an agent need the bridge transform? Yeah.
So what it basically does is it turns your joint belief over computation and the way the world is to something like a belief about how computations are, combines with which computations the world actually computes. So you can be like, the world runs this computation and this computation, but not this one.
Gotcha. So it's a way to see all of the, is it correct to say that the bridge transform gives the agent a way to see all of the programs that are currently running in the environment?
I would generally say that there are some complications with monotonicity, but yeah, the general sort of insight is that if for different states of the program, physics behaves pretty much the same, then you can be like, this program is probably not being run, or if it is, it's having no effect whatsoever on like what's actually going on. But if you find a program where its state is correlated with the world, that you would expect the program to behave in a similar way to how some part of the reality behaves, then you can be like, reality is running this program.
And that allows the agent, which is a program, right? The agent itself is a program. It allows the agent to locate itself in the environment. Is that accurate to say?
I think I would say so. If you had a hypothesis where its state, if you had a hypothesis where it's basically like, oh yeah, no matter what this agent program spits out, reality is going to keep chugging along in exactly the same way, then you might as well completely ignore that hypothesis because nothing you do has any effect. So yeah, what's left over is the hypotheses where it's like, yeah, I would expect reality to go differently based on how this computation, i.e. the computation that is the agent, turns out.
Got it. So if I could just summarize infra-Bayesian physicalism as I see it right now, and then you could maybe fill in any holes in my understanding here, or just interrupt me if I say something that sounds incorrect. Normally, when we're doing reinforcement learning, we have agents who it's assumed that they occupy some special state in the universe, or well, actually backing up just a little bit. So normally when we're doing reinforcement learning, the hypotheses of our agents is phrased in terms of that agent's subjective experience. And that is a very complicated hypothesis. And we would like to have...
It's more like, I'd say, hypotheses that are, in some sense, objective versus hypotheses that are subjective about your personal experiences. They have different notions of what counts as simple versus complex. Like throwing a towel over the webcam is something that is pretty simple subjectively, but objectively maybe not quite so much. While something like I see, while a hypothesis that's like, I'm just going to see black forever, that's very simple to specify subjectively, but objectively it'd be like, what? Why would there be a law of physics that says the universe poofs out when somebody throws a towel on the webcam? So I'd say that subjective versus more third-person hypotheses tend to have different things that they say are simple versus complex.
Got it. So infra-Bayesian physicalism gives us a formal way to specify these hypotheses that are bird's eye view hypotheses. Are nice. It's nice to be able to come up with bird's eye view hypotheses, and then to use the bridge transform to turn these bird's eye view hypotheses back into something that the agent can use from its subjective experience to figure out how it should behave.
Yeah, and also it can give the agent like information about, hey, here are some computations you might want to run to find out about the environment. Basically, pointing at interesting things to think about while you're in your metaphorical AI armchair. And if your hypothesis is like, this computation is correlated with this part of reality, and you do the computation and you look at reality and it's not what you expected given the computation, then you're like, huh, guess that hypothesis was wrong.
Yeah.
One of my questions that I asked Vanessa was something like, wait a minute. So if some weird simulation of like some n particle simulation with gravity is like correlated with some obviously non-gravity thing, like how a flower behaves somehow, then isn't it really weird to say that reality is running that gravitation simulation? And Vanessa made the really interesting point that, like, if there actually was a gravitation simulation where checking on it reliably told you information about the flower, then yeah, it actually wouldn't be too weird to say that reality is implicitly running that n particle gravity simulation.
Gotcha. Now, I will have plenty of opportunities to ask Vanessa about this next thing, but if you have anything to say here to add that might be of interest to listeners, that would be great. Information physicalism has a lot of uses. One of them is that Vanessa has recently been tinkering with an alignment protocol of a full path to solving both the inner and outer alignment problems that she thinks might be rather promising, that leverages information physicalism, and she calls it PREDCA, or pre-DCA. Do you have anything to add here? Want to chat a little bit about what PREDCA is, how it draws on information physicalism to solve the alignment problem?
Not so much. I would say that Vanessa is substantially more optimistic about the applicability of physicalism than I am. I mean, I helped out with the math, wrote up the theorems, but I would regard Vanessa as being substantially more optimistic than I am about whether the physicalism stuff like really pans out and like a deliverable.
Got it. So just a few more questions here. We'll kind of zoom back out from information physicalism. We'll get out of the weeds a little bit and just get a little bit more big picture. What research is currently being done to advance informationism?
So Vanessa currently has a paper that she's working on about infra-Bayes bandits, basically trying to generalize the n-armed bandits problem out of the realm of standard probability theory to come up with some algorithm that works when you can just figure out properties of the bandit, or maybe even like a time varying bandit or an adversarial bandit, just as long as you can find some constraints that this thing obeys, doing pretty good. So that is sort of the latest that she has been working on. It's a bit complicated with the proofs and error analysis, but it seems to do pretty well.
And how would you like to see research on informationism advance in the coming months and years? What progress do you hope happens sooner rather than later?
I think that probably awareness of it as a tool that might or might not help, but hopefully does. I think probably one of the things I'd be happy to see is the occasional other person being like, oh, hey, this other thing I was working on, the natural fit for it is not standard probability theory, it's this thing, and I'm especially interested for any sort of value learning protocol with it that can just get fairly good coverage over a set of possibilities instead of optimizing really hard for one.
Is there any research direction in particular that you have a hunch might benefit from using infra-Bayesianism rather than standard probability theory?
So as I previously said, I am a bit more optimistic about the value learning stuff. I think that there might also be okay, so although it seems obviously applicable to like multi-agent dilemmas and game theory and stuff. I don't actually think the theorems proving good behavior are really there yet. So that feels more like something I could possibly work on. And I think that in general, any sort of AI thing where you're like, dang, it'd be really convenient to have something more cautious than standard probabilistic reasoning, or something that treated the environment more adversarially, or that sort of thing. Just like, hey, there's a tool. It might work for your situation.
Yeah, got it. Those are really all the questions that I had, but I want to give you some time and space here. If you would like, if there were any questions that I didn't ask that I should have asked, anything else about Infra-Bayesianism that you would like for people to know, anything else you'd like to communicate to people about Infra-Bayesianism?
Oh, I guess from a purely mathematical point of view, it's pretty interesting because it's okay. So for wait, hang it. Actually, it's a bit obscure, but so for a lot of abstract computer science stuff, they really like their lattices or partial lattices, or that sort of stuff for like abstract program semantics. And there's the cool thing that infra-Bayes stuff meshes way better with that whole area of math than standard probabilistic stuff. So yeah, that's one of the interesting things, is that it's a very well-behaved sort of type. But yeah, don't really have too much to add, I guess.
No, yeah, that's fine. That's fine. If someone were if someone after watching this felt that, oh, I feel like I would be a really good fit to work on Informationism, how would they get started? Like, was there anyone that they should reach out to you? Should they reach out to you? Yeah, how would they get started on that path?
I think probably reaching out to me or Vanessa. There's also one thing I probably want to point out. There are enough people who have been like, yeah, distillation, yeah, packaging this up for other stuff, that I would say that we're pretty saturated on that already. But in terms of people being like, hey, here's my pet interesting math thing, maybe I can poke at how this connects, then yep, hit up either me or Vanessa.
Yeah, I'm one of those people who's saturating that distillation market. So, I appreciate your mentorship on this distillation project, and I appreciate your time here and for chatting with me. So thanks so much.
You're welcome.